we were talking about energy and activation energy and things. There's a huge amount of energy exchange going on in a chemical reaction. Okay? And we're talking about heat energy. Okay? We call this thermodynamics. Okay? But before we get into that, let's discuss a few other terms that we, may not remember or have talked about, but where it is in reference to chemistry, because like kinetic energy and potential energy, I'm sure you've heard of it in physical science. But now we're going to really narrow it down in how it applies to chemistry here. So kinetic energy is the energy of motion. It says that right here. So we're looking at how fast particles are moving. So if we have, like, say, for instance, our like solids versus our liquids versus our gases, our three phases of matter that we typically talk about. Which one of those phases is the kinetic energy of the particles the highest? Which one has free-flowing, moving particles? Gases do, right? So the kinetic energy of gaseous particles is really high in comparison to, say, solids, where solids are in like a nice fixed position where they just vibrate in place. That's all they do, is they vibrate in place. Now, of course, this is at a molecular level where we can't see it with our eyes, but they are actually moving slightly. And then, of course, the middle phase liquid has some free-flowing. So the particles move around a little bit more freely than a solid, but not as much as a gas, okay? And if you remember from Unit 4, the reason why like liquids hold together and can form the shape of their container is because they have some intermolecular forces holding them together, those dipole-dipole, those dispersion forces, or if it has, H-bond, it's going to have some hydrogen bonding like water, okay? So intermolecular forces holding it together really tightly makes it a solid. Intermolecular forces holding it, some intermolecular forces can change it to the liquid, and then when you break all of those forces, now you have gases that bounce off the walls and are just free floating and moving all the time. So that's where our reference to kinetic energy is looking at for chemistry. Now let's talk about potential energy. Who has a reference for potential energy? Yes. No, it could be any reference for potential energy.
So like when you think of someone who has potential, you think of someone who like is able to do something, but they kind of like store it up a little, like they keep it. So
yes, no, I agree with that. Potential meaning like you have the ability, yes, and it's sitting there waiting to do something. Yes, Adam, you have a different one?
Well, like potential energy is basically energy stored in an object or a person that is waiting to be used or consumed.
Okay, good. But does anybody have like an analogy? That is pretty much exactly what she said too.
Like a ball waiting to roll from the top of the hill.
Yeah, the ball at the top of the hill waiting to roll down. Yes, that's the physics type reference that we all normally get. That's what I was kind of going for, but yeah. So it's waiting there. It's ready to move. It's got all this potential to have, start moving. But when we're talking about chemistry, where is our potential energy going to be located? It's going to be stored in the chemical bonds. Chemical bonds, that's where our potential energy is. So when you eat food, what is your stomach and when you chew on it and your enzymes doing? It's breaking down those bonds. And when we break those bonds, we get little bursts of energy, and then it goes into our mitochondria and all this stuff, and it makes all these ATP molecules, right?
Adenosine triphosphate or something.
Adenosine triphosphate, exactly, ATP. So, where we're looking at in terms of chemistry is not the ball rolling down the hill. We're looking at potential energy being stored in the bonds of our chemicals. So those covalent bonds, those ionic bonds, that's where we're looking here, okay? Now, those chemical bonds, when they break, they give off bursts of energies. When they form, they release energy too, okay? So there's a whole energy exchange going on in bond breaking and bond forming. And we're going to be looking at two types of reactions that can occur here. We've got exothermic and endothermic.
Exo means it's going out, endo means it's going in.
Yes, we say exo means exit, like it's releasing energy. Energy is released. I've also heard somebody say, forming is warming, because in an exothermic reaction you have bonds or forces forming, So it's going from an unstable state to a more stable state. You're going to have, some releasing of energy. It's like that relief. You're getting relief now that you're back to being stable. So you're releasing some of that pent up energy. Okay. I've also heard axing is taxing. So like if you have to break bonds, you're axing the bonds. Breaking bonds takes energy, right? So taking energy, absorbing energy would be endothermic. Axing is taxing. So endothermic, you have to break bonds, so it requires energy to do so. Keep that in mind now. In reactions, you can see this written in this particular manner. So say we have a reaction, X squared, or X, a diatomic molecule, and we're going to make 2xy, right? If we have heat over here as a reactant, heat is a reactant. That means heat needs to be absorbed for this reaction to take place. So in this particular case, if heat was a reactant, this would be endothermic. Okay? You need heat in order for it to work. How about here? Say we had the reverse, or we had this going on. A plus B gives you AB. But heat is being released as a product. So if heat is on the product side, like so, this one would be exothermic. Heat is leaving the building, exiting. Okay, you could think of it that way. Also, what you should think about here, too, in terms of the idea of endo is confusing to people. But everybody go ahead and take their hand and put it on the table. How does that feel to you? It feels cold, right?
What?
Endothermic reactions are going to feel cold, and exothermic reactions are going to feel warm, okay? But what is actually going on here when I put my hand on the table? The table is taking heat away from my hand. It's transferring energy from my hand into the table. So it's absorbing energy from my hand. That's why it feels cold to me. Okay? Now here I touch my face. Guess what? It feels warm because what is my skin doing? It's releasing heat into my hand. So that's exothermic. I'm feeling exothermic here when I feel warm. Okay? So keep that in mind. Now for the diagrams themselves, and yes, there'll be one on your test, and make sure you learn these. These are not hard if you just learn where every piece of information on them goes. The first part of the potential energy diagram. The energy diagram looks like this. You're going to see like two flat lines, a little hill, and so forth. Okay? So, potential energy is on the Y, and then like the reaction progress or time is on the X. The first line here, this flat line always on, if we're talking about the forward reaction, which that's what we're going to be referring to right now, this is always going to be your reactants. So that refers to A down here is the potential energy of the reactants. That is the amount of energy stored in the reactants, chemicals, bonds. Okay? So what is in the bonds of the reactants? That's how much energy is in there. Now, over here on the right, this guy, this other flat line is now the potential energy of the products. So that's how much energy is left in the bonds of the products when we're done, all said and done with the reaction. Okay? Now, as before, we identified the hill part as the what? What's the hill part? What do we call that big hill part? It was just what we talked about a minute ago on our other sheet. It's not, well, activation energy, yes, we can look at the hill to figure that out, but what is the hill called where it's that transition state? We have all those intermediates going on, bond breaking, bond forming.
Activated complex.
It is the activated complex. Very good. Activated complex. So that's that transition stage, that part of the hill. Okay, yes, you'll use the hill to figure out your activation energy. In just a minute, let's look at that. So this amount of energy from the bottom to the top of the hill is our activated complex. Now, The other little tip, well, there's two other things you can identify on the graph. And yes, let's bring up activation energy. The minimum amount to get it started. The minimum amount to get it started is from the amount that you have in your reactants to the top of the complex. Okay, so this is my activation energy. How much do I have already to begin with, and then how much more do I need to get it started? The difference between those two is going to give you your activation energy. Okay? And last but not least, we need to talk about delta H, heat of reaction. This is also known as delta H, the change in the heat. Okay, delta means change of. So the little triangle is a delta. It's the change of the heat. Now, this is basically how we calculate it, the basic gist. It's going to be the heat of the products minus the heat of the reactants. Okay? Your delta H is going to be the heat of the products minus the heat of the reactants. Now, another word we use for delta H sometimes is enthalpy. So if you see a word that says enthalpy, it means delta H, or heat of reaction. Enthalpy, delta H, heat of reaction all means the same thing. Okay? Now, so on here, the heat of reaction is the products minus the reactants. What you will see here is you need to make a little line across for your reactants, make a little line across for your products, and the difference between these two is your delta H. Now, it's products minus reactants. So looking here, our product line is lower. So if I do products minus reactants, what kind of number am I going to get? A negative number. That's correct. So products minus reactants, if I get a negative delta H, like over here, because my products minus reactants will give me a negative delta H, then I know the reaction is exothermic. Exothermic when my delta H comes out negative. My products line, my amount of energy in the products is now lower than what I started with. That means some of the energy had to be released to the environment. That's why it's exothermic. Because where did that energy go? It went to the environment. We feel the warmth. Forming is warming. Forming the bonds made it warm. There you go. But if you look at this example over here at this diagram, here is your reactants. Here is your products. Here is the activated complex. Here, if we did products minus reactants, what would our delta H be? This time, it would be a positive delta H. Good. So this diagram where the product line is higher is going to be what type of reaction? If that one was exo and negative, this one's going to be endo, and delta H is positive. Okay? Now, the only other thing that you might see on a diagram that I haven't talked about, okay, is if we have a catalyst. What did we say a catalyst does again? Catalysts do what? Speeds it up by lowering the energy required to make the activated complex. So we could say it lowers the activation energy. Lowers the activation energy. So how would we represent that on a graph, though? What would we need to lower on our graph here to make it show that a catalyst is involved? Where is our activation energy? Goes from the reactants to the top of the hill, right? That's our activation energy for this one. As you see, the endothermic reactions, their activation energy is much higher. But if I added a catalyst to it, guess what's going to happen? This part is going to be lower. So if I added in a catalyst, my little hill now becomes shorter because now my activation energy is going to go from here only to about there. So if you see if the hump has been decreased, you can see that a catalyst was added to the reaction. Okay, because we lowered that activation energy. So now, let's go ahead and take a look at your example and work through some of them. The next page. And I'm going to help you identify some of these letters because they're hard to read. This is an A, this is a B, this is a C, D, E, and F. Okay? To help you identify those lines a little bit better because they're kind of hard to read those letters. This is X plus Y. These are our reactants making Z. So our reaction is X plus Y giving us Z. That's our, generic equation. Okay? So, which of the letters A through F, based on what we just looked at, and you can go back and flip back to it. That's why they're notes, for you to look back and review. Okay? Which one represents the potential energy of the products? So where is my product line here? Is it over here? No, it's going to be on the right side. You're right. Here are my products, right? Products. So what letter is the going from products all the way down to the bottom? That would be E. Good. Now, which letter indicates the potential energy of the activated complex? Where's the activated complex again? Top of the hill. Good. So top of the hill, all the way down, that's going to be what? That one's actually C. D actually stops here at the dotted line. Okay. So this one's going to be C. Good. Which letter indicates the potential energy of the reactants now? So over here, remember the first line, the first flat line, that's your reactants. So that's going to be A. And which letter indicates the activation energy? Activation. Activation goes from the reactants, remember, all the way to the top of the hill. So that's going to be B. Very good. Now, which letter indicates the heat of reaction? Remember, heat of reaction is delta H. Okay? Which one's going to be delta H? F, because we have the products minus the reactants. This is the reactant line. This is the product line. So in between, that's going to be your delta H. So that would be F. Which is the reaction exo or endothermic? It is endo. How did you know that? It is definitely endothermic. How do we know that? The what? Yes, what is higher than, what's the higher one? Products are higher now, right? Products energy up here is higher than the reactants. So you know you're going to get a positive delta H. You know that you absorbed energy into the products. So therefore, it's going to be endothermic. When you see the products higher, it's endo. When you see the products lower, it's going to be exo. Okay? Now, one other quick thing they might do to you. Look at number 7. Let's see what number 7 means. What did they throw in there? Reverse reaction. What does that mean? So we're going to go backwards, exactly. So now, guess what you can do? Sometimes you can have a double arrow, and it can go the other direction. So if we go the other direction, what now becomes the reactants? Who becomes the reactants now? Z is now the reactants. If we're reversing the reaction. Okay? You reverse the reaction, Z becomes the reactants, and then XY over here is going to become this is going to become the product in the reverse reaction. So, let's see what we got going on here. Which letter indicates the activation energy of the reverse? What is activation energy again? Minimum energy, so where do we identify that on the diagram? From the what to the what? Reactants to the activated complex. Good, I see that. Reactants to activated complex. Where are reactants right now? Our reactants are now over here, right? To the activated complex, what letter is that? That would be D now, because we're going the other direction. Which letter indicates the heat of reaction? F is still the same, if you notice, because it's the product, the products over here minus the reactants, still the same amount. Okay, so that's going to be F. And is the reverse reaction exo or endo? It is exo this time because the products are now lower. Products are now lower than the reactants. You're going to get a negative delta H. Okay, it'll be the same number, but it'll just have a negative sign in front of it. So let's work with some numbers here. Let's take a look at some numbers where it actually has numerical values on things. So looking at this potential energy diagram, heat content of the reactants. And this is in kilojoules. You could also see them that having kilocalories, because those are two measurements of heat. So heat content of the reactants is the forward. Which one's the reactant line? The one on the right or the one on the left? The one on the left, right here, reactants, right? How much do we have for our reactants? 80. Now, how much do we have for our products? 160. Good.
What is that?
Kilojoules. Joules is a measure of heat. Kilocalories could also be on there, or calories. You might see them. What is the heat content of the activated complex? Activated complex, top of the hill, all the way down. What's that? 240. Good. How about the activation energy of the forward, going in the forward direction? Where do we go from? Reactants all the way to the activated complex. So we need to do a little subtraction here. What's that going to be? 240 minus 80. So that's going to give us 160. Good. Heat of reaction of the forward. Remember, heat of reaction is going to be H of the products minus H of the reactants. So our products is what? 160, right? What's our reactants? 80. So therefore our heat of the forward is 80 kilojoules, and it's a positive 80.
Degrees.
All right, so is the forward reaction going to be endo or exo? Endo, because it's a positive delta H. The product line is higher. Very good. That's what we got going on. Now the heat content of the reactants of the reverse. So who becomes the reactants now? The products that were, once we're the products are now the reactants because we're going the other way. Okay, so we have our value to being 160, right? Heat content of the products is going to be now 80. Heat content of the activated complex, does that change? No, that's still what? Activated complex is going to be 240. Now, this is the one that does change, the activation energy. because the activation energy going reverse is from here to here. So that's going to be what? 240 minus 160. So our activation energy is only 80 kilojoules. That one takes less going the other direction. What is the delta H here? Still going to be products minus reactants, but our products are what? 80. Our reactants are 160. So what kind of value am I going to get there? A negative 80 this time. So you got to have that negative sign. Okay, then that tells us it's going to be what type of reaction? Exothermic. Very good. It's exo. Exo versus endo for the forward. Okay. One other quick thing on the next page before we call it a day, or well, actually, you guys can continue to practice. I wanted to show you this one part. On this page, this is the page I wanted to show you. What are you supposed to write here? For the term, like for A, what is A? We would put PE, potential energy, you can abbreviate, of the reactants. That's what you would write here, okay? Now, a description of the potential energy of the reactants. What does that mean in word form? That is how much energy is located where? In the bonds of the reactants. Very good. So this is the amount of energy in the bonds of the reactants. So that's how I want you to describe this part, okay? That's what you're supposed to be filling in there. Does everybody kind of understand what I want for that section? Okay, the rest of this packet will be homework. Okay, so make sure that you finish that. But we still have 7 minutes, so you can answer some more questions. Okay, get some more done. On the bottom part, make sure when you draw down here, okay, make sure you use your letters and label. Okay, and you want an endothermic reaction. So how should you draw those product reactant lines? Think about that. How is the endothermic one going to look? Okay? Any questions?